When atoms have unpaired electrons or lonely electrons, they are unstable. That's not an ideal situation. So they will want to get a partner for all of those unpaired electrons, and this is going to bring us into the topic of chemical bonds. There are different types of chemical bonds, and we'll talk about some of those types. One type, probably the most common type, is going to be what we call a covalent bond. With a covalent bond, you have two atoms that are sharing electrons with each other. The electrons that they share are going to be found in the outermost shell, and that's what we call the valence. So the valence is just a term, just to sum it up or review it right here. It is going to refer to the outermost shell, and that outermost shell is where we would find any lonely electrons if there were any lonely electrons. Okay, so when atoms do actually share electrons with each other, they will form that covalent bond, and we have different levels or different types of covalent bonds depending on how many electrons they are sharing with each other. We call this structure that we get at the end a molecule. So the molecule is going to be two or more atoms that are sharing electrons with each other, or in other words, are held together by covalent bonds. And a single covalent bond will be if they are sharing one pair of electrons. So to share one pair of electrons, this atom would share one electron with this atom over here. So each one of these is sharing one with each other, so they're kind of holding on to that electron from the other partner. A double bond is very similar, but a double bond is sharing twice as much. With a double bond, you have two electrons from this one and two electrons from this one, and they're sharing with each other right in the middle. Still going to be two atoms that we have involved in this, but again, we are sharing more electrons, two from each, 4 electrons total. Now, if we look at some pictures that show us this sharing of electrons. In the first picture here, we have two hydrogen atoms that are forming a covalent bond, specifically a single covalent bond. This hydrogen over here and this hydrogen over here both have one lonely electron, and so that lonely electron they're going to share with each other so that you will have a pair. Each one of them has a partner next to it, and that's a single covalent bond, and that's what we call a hydrogen molecule. We're going to call it a molecule now because they are connected together by sharing those electrons. We can do the same thing with two oxygens. The picture is drawn a little bit different here than the electron configurations we looked at before. But if we just think about the fact that oxygen would like to fill up that second shell, to fill up the second shell, oxygen needs 8 electrons out there in the ring. So this oxygen over here has 6, this oxygen over here has 6, and they're going to share 2 each with each other. So if this oxygen has 6 and 2 more come in and are shared with it, it's going to have a total of 8. And same thing for the other one. So if we look at these guys over here, notice that each oxygen has 8 electrons on the outside. So 8 electrons in the valence shell is the way that we would refer to that. That's a double bond, and you can see that right here. If I just draw it a little bit bigger, we represent those bonds as a line. So if it's double, we're going to put 2 of those lines. We can see the same thing, same idea in the next one. And the next one, we have one carbon atom that has 4 electrons that need a partner, or in other words, it needs 4 more electrons to make that full valence shell. And the way that it will accomplish that is it's going to surround itself with 4 hydrogen atoms. So this molecule over here shows that carbon is making 4 separate single covalent bonds. And one of the reasons why we will find carbon in so many molecules and in so many different configurations is because carbon is unique and that it has the ability to share those electrons with 4 different partners. So sometimes we'll see it sharing with 4 hydrogens, sometimes we'll see it sharing with 4 different atoms or 4 different elements. On the bottom picture, we're seeing where we have a carbon that is sharing electrons with 2 hydrogens and then also with 1 oxygen. And again, the end result of this, or kind of the goal of this, would be for carbon to get 8 in that outside shell, that valence shell. And if we can get 8 electrons in the valence shell, then that will make for a very stable carbon atom. So down there you can see formaldehyde is the example that we're showing. Okay, so we're sharing electrons. The idea behind sharing electrons is that we want to fill up the valence shell, but sometimes the atoms do not share well. And electronegativity is the property that we say specifies how well they're actually sharing electrons with each other. Electronegativity, by definition, is the attraction of a particular kind of atom for the electrons in a covalent bond. So basically, these electrons that are on the outside, they have a negative charge, and the nucleus has a positive charge because of the protons that are there. And so those electrons are going to be attracted to that positive nucleus. Opposite charges always attract, and depending on how strong the nucleus is, it's going to be sucking or pulling those electrons in with a lot of force. So the way that I like to visualize this is that it's like a tug of war. And if you think about a tug of war, you've got two people, they are pulling on a little rope between them, and there's a knot in that rope. And if we have two individuals that are equally matched, so they have equal strength, two big ones or two wimpy ones, either way, if they have an equal strength, that knot in the tug of war is going to stay right down the middle. Nobody's winning, nobody's losing. Sometimes that's the way that our sharing goes when we're talking about the covalent bonds. But if we have one that's really big and we have one that's really wimpy in our tug of war, we would expect that the big one is winning. And the big one would be pulling that knot in that rope much closer to themselves. So that would be unequal sharing of the electrons because one is so much stronger than the other. Well, the periodic table is organized somewhat according to the strength or the electronegativity of an atom. And you can see some shading here in this picture that shows you kind of groups of strength. If we focus on the ones that we're going to see a lot this semester, we've got oxygen and carbon right here, and they're both yellow, and yellow is pretty weak. So carbon and hydrogen are not very electronegative, or we call them weak. So that means they're going to be like the little guys when we're talking about our tug of war. And then our other two elements that we're going to see a lot, I've kind of covered it up, but they're right here. That is nitrogen and oxygen. Nitrogen and oxygen are strong and pretty equally strong with each other, and they will be like the big strong individual in the tug of war. So if we keep this in mind, we can get an idea of how well electrons are sharing, or atoms are sharing, when they're participating in these covalent bonds. So we'll have an idea of whether those electrons are being shared right down the middle or whether they're being shifted and pulled towards a really strong atom. And so if it's kind of pulling them away from a weak participant. We have two different names for our covalent bonds depending on how well the sharing is going. And again, this is all about the strength of the participants in that particular sharing. The polar covalent bond is what we call it if the atoms have different electronegativities. So if one is really strong and one is really weak. So again, if one is strong and one is weak, the strong one is pulling those electrons over towards itself. All right, let's draw this here, similar to the example that we just gave, so that you can visualize this a little bit better. The polar covalent bond is going to be like this. You've got one that's really strong and you've got one that's really weak. And so the strong one is going to be winning or pulling those electrons much closer to itself. So there's not a good sharing situation going on. The nonpolar, on the other hand, this is when you have two atoms that have similar electronegativities, and if they're similar in their strengths, they're going to be sharing those electrons equally. So to draw the picture over here, here's two individuals that have an equal strength to them or an equal size to them, and if they have an equal size, the electrons are right down the middle. They're not being shifted one direction or the other. Now, the reason why this is important is because this does affect overall properties of the molecules that we look at later. This is a picture of a water molecule, and water is extremely important inside cells. And one of the things that gives water all of its unique characteristics is the fact that it's made of some bonds that are polar. So we have oxygen in the middle here, and if I just draw this out so we can also see it here, oxygen is one of those really strong ones. So the idea is that we've got this strong participant here, and then we've got this wimpy guy over here, and we've got a wimpy guy over here. And we're trying to share electrons between them. So if this is a rope and this is a rope, in both cases, oxygen's just kind of pulling in those electrons towards itself because it's not sharing very well with those two oxygens that are on the sides of it. What that does to the molecule is when oxygen's pulling the electrons towards itself, it's also pulling negative charge over towards itself because the electrons have a negative charge. So we will see this area, and we see it right here. This is an area of negative charge. And at the same time, because we're pulling negative in this direction, that's going to leave the little wimpy ones, our hydrogens, with areas of positive charge because their electrons are being pulled in another direction. So down here with our two hydrogens, we can see an area of positive. Anytime we have polar covalent bonds, we will get an area of negative surrounding the really strong one, and we will get an area of positive surrounding the really weak one that we have. If we happen to have non-polar covalent bonds, then you have this nice neutral coverage of charges over the surface. So we won't have an area of positive, we won't have an area of negative. It'll just be neutral. Another type of bond that we have besides covalent bonds is going to be ionic bonds. Ionic bonds are going to happen when two atoms are so unequal in their electronegativities or their strengths that one atom is going to completely strip or pull an electron off of its partner. And if we look at this picture, sodium right here is very weak and chlorine is very strong. And as they're drawn in this first picture, both of them would be considered unstable because both of them have a shell on the outside that is not filled up. So they don't have 8 in that third shell, which is what they would really like to have in the third shell to make them stable. So chlorine is so strong, it actually pulls an electron right off of the sodium. And when it pulls that electron and takes it away from the sodium, what that's going to do is it's going to give chlorine the 8 that it wants in its outside shell or in its valence shell. And that's going to give sodium just a second shell on the outside. And sodium's second shell on the outside is going to now be filled up because it's going to have 8. So at the end, when all is said and done, sodium has a positive charge and chlorine has a negative charge, but both of them are very stable. When they do that, what's going to happen, so we've moved the negative charge over, but opposite charges attract, and this positive one will be attracted to the negative one, and they'll basically just stick together. So opposites attract. That is a theme that we want to keep in mind for the entire semester. So opposites attract, and we're talking about positive is attracted to something that's negative. So the two are going to stick, and that sticking is your ionic bond. So the ions are charged atoms. That is what we just drew on that previous slide. So if you have a sodium that has an overall positive charge, that is an ion. If you have a chlorine atom that has an overall negative charge, that is considered to be an ion. We can classify ions depending on whether they have a positive or negative. If they have a positive charge, we call them cations. And if they have a negative charge, we call them anions. Okay, so those are just two specific ways to talk about ions or describe ions. In our example, the sodium had a positive charge, so the sodium was the cation, and the chlorine had the negative charge, so it is the anion. When we look at salt, salt is just a arrangement or crystalline arrangement of negative chlorines and positive sodiums. And so that's the grain of salt that you put on your food. Well, this is going to be something that water can dissolve really easily. And the way that water is going to dissolve that is water has that negative end, which we can see right here, and the negative end of the water will surround the positive sodium. And so it will just orient itself so that you get this little coat of water molecules on the surface. And for the chlorine, since it has a negative charge, the water is going to turn itself in the other direction so that you have the positive end of the water molecules surrounding that. And again, you get a little coat on the surface. So ions are going to be things that are very soluble in water, or they can dissolve in water, which is an important property of water, the fact that it can dissolve various substances. So just to review, we had two types of bonds that we've described. We have covalent bonds and we have ionic bonds. And we see the two pictures here, and the main differences between them is that covalent is sharing. Okay, that is the key word for covalent bonds. They are sharing electrons between two separate participants, so they are kind of linked together by that sharing. The sharing's not always equal. It can be unequal, and if it's unequal, we call it a polar covalent bond. If it is equal, we call it a non-polar covalent bond. On the other side, we've got our ionic bond, and the ionic bond, a lot of times there is an entire shift of an electron or a movement of a negative charge, and then we're left with an ion that has a positive charge and an ion that has a negative charge. And if you have an ion with positive and an ion with negative, so a cation and an anion, those two will just want to stick together because opposite charges always attract. One last bond type to talk about and describe is going to be the hydrogen bonds. Hydrogen bonds are bonds that are formed when a hydrogen atom with a partial positive charge, so a region of positive around it, is attracted to an atom that has a full or partial negative charge. This is something that we see very commonly when we're looking at water molecules. Typically, water molecules are not all by themselves. They are in the presence of other water molecules. And if we look at this picture right here, this hydrogen, it has a little area of positive around it, and it would be attracted to this oxygen right here, and we can see this as the double or the little dotted line. It's going to be attracted to this oxygen because opposite charges attract. That is a hydrogen bond. So what you see is that all of these hydrogens are bonding to the oxygens of nearby water molecules, and it creates all these links between water molecules. This is important for a lot of the properties of water. This is going to provide surface tension. If you've seen leaves floating on the surface of water, that's the reason why. Because the water on the top is all linked together in these relatively weak interactions, but they are connected together, and it is enough of a connection, a strong enough connection to allow a leaf to float or an insect to walk on that surface. Now, another example is over here. If we look at this example, we can see that, again, we have a hydrogen right here, and it is attracted to this oxygen over here that has the negative charge. The reason I'm showing that one is because I want you to understand that it doesn't just happen between two water molecules. This can happen between other things that don't involve water. We just need to have a hydrogen that has a positive charge to it, partial positive, region of positive around it, and it's going to be attracted to something that's a little bit negative.